As COVID-19 coronavirus cases are on the increase all around the world, and with school closures, our students are really suffering. And educators are scrambling for ways to help the students with their education. And I thought, well, maybe I can help by putting lectures on tape and see how it works. And I tried to secure a classroom setting, but I was not given permission. And I'd like to thank Light for All Nations for making their studio available. And I'd like to thank them especially for coming in on a Sunday. Today is Sunday, the 22nd of November, 2020, and giving of their time. I'd like to thank Manal and Joseph Silwanis, Mina Wasif, and Reverend Nizar Shaheen. Thank you very much. Now, my wife suggested we call this Physics for All. I added the word international because we might be seen all around the world with students trying to study from home. My name is Naeem Gaid. I used to teach physics, but I have now been retired for 21 years. So I'm going to try to remember my physics. And if I make mistakes, I apologize. Just remember, your teacher has the last word. I also added my email address, and I wrote it more clearly down here, just in case other retired physics teachers would like to come out of hibernation and help. And as a matter of fact, I have a math teacher who lives on our street, and she's retired, and she said she would be interested in a program like this, and she might be able to help in math. So this is a trial lecture. If it is well received, if we get a good response, then we can put on more lectures. There's only one problem. In physics, we do a lot of problem solving, and I'm not following a textbook. So because I'm not following a textbook, I can put our notes with problem solving, and our notes, and I say our because there's a co-author, and I have to secure his permission. And I believe there are about, if my memory serves me correctly, about 438 pages of physics notes with problems, solutions, and answers. So this trial lecture, I chose a topic: work, energy, and power. I will cover the work, energy, and power topic completely, I hope. But at the same time, I have to go back and review some of the work. And as I said, if there's a good response, I can put our notes on the internet. I don't know how, but other people who know can help, and we see how it goes. Now let's get on with the subject: work, energy, and power. I will start with work, then power, and I will finish off with energy. In physics, work is defined as force multiplied by parallel displacement. So if you have a force applied on an object and it is displaced, you simply multiply the force times the displacement, and you get your answer in Newton meters or joules. If you lift an object that weighs 50 newtons and you lift it 2 meters, then the force is upwards, 50 newtons. The displacement is 2 meters. You multiply 50 times 2, you get 100 Newton meter joules, and you get your answer. Who said physics is difficult? It's very simple. That is if you're lifting the object. But what if you are moving with the object? If you are moving with the object, you're applying a force upwards, because if your hand is not there, the object will fall. So the force is upwards, and the motion, if I go move like that, then force and displacement are perpendicular. There's no work done. No work done. And if we plot the force displacement graph, notice that if you multiply the force by the displacement, you get the area under the graph, the area of a rectangle. Now this is a very important concept that I will be going back to later. The area under the graph, the force displacement graph, gives me the work done. What if this force is applied to the object at an angle theta to the horizontal, and the object moves? Well, we cannot multiply the force by the displacement because they are not parallel. What we do in this case, we resolve the applied force in the x direction, Fa cos theta, and in the y direction. Well, in the y direction, Fa sine theta, you will notice that this force is down, Fg, which is mg, is down, the normal force is up. Forces going up must equal forces excuse me, forces coming down. So the absolute value of the force up is equal to the sum of these two forces. And this force is parallel to this displacement. So all I have to do is multiply this force by this displacement, Fa cos theta times the displacement, and I get the work done. Also, we said that the area under the force displacement graph gives the work done. What if the force is a variable force, whether increasing or decreasing? Well, I get this, which is a trapezoid. I get the area under the trapezoid. F1 plus F2 divided by 2 times displacement. And that's the area of the trapezoid, A plus B divided by 2 times H. What if the force is a straight line like that? Well, the area under the graph is the area of the triangle. What if the force is a power graph like this? Well, again, the work done is the area under the diagonal. And we'll talk about that later on. Now we'll talk about power. I want to lift 50 newtons, 2 meters. So I get a machine. And the machine does the work for me. Zzzz. How much work did it do? Well, if the object weighs 50 newtons, it has to apply 50 newtons. And the displacement is parallel, 2 meters. So it did 100 newton meters or joule. I get another machine. Zip. How much work did it do? Well, whether you apply the force slowly or fast, it makes no difference. It still has to apply a force equal to the weight, 50 newtons, times 2 meters. So 100 newton meters joules. My question then is, which is the more powerful machine? Obviously, it's the second one. Why? It did it in less time. So power then is the rate of doing work. I flipped 2 pages instead of 1. Here we go. Power. Power then is the rate of doing work. Power is work divided by time. The units, Newton meter per second, joule per second, or watts. Some books refer to horsepower. Well, 1 horsepower is equal to 746 watts. If you want to get the efficiency, it's power output over power input. And in percentage, power output divided by power input times 100, that gives it to you in percentage. We're done with work and power. 2/3 of the chapter in any textbook. Now we go to energy. Imagine a boy and a girl sitting under an apple tree. Now this apple is above their head. Because of its position, if it falls, it will do damage. Well, what is the definition of energy? Energy is the ability to do work. The ability to do work. Energy cannot be created or destroyed. Energy is the ability to do work. It is conserved. We don't lose it. It changes from one form to the other. It cannot be created or conserved. So this example that I gave you of the boy and girl sitting under an apple tree, the apple could fall because of its position. And it could cause damage. Hopefully not to the relationship. So if this apple falls, it will fall because of gravity. So it has energy due to its position And if it falls under the effect of gravity. We call this gravitational potential energy. Now let's try to come up with a formula for it. Here's the apple. Here's the mass. The force of gravity is mass times gravity. The displacement, I'll call it h. Force multiplied by parallel displacement, mg multiplied by h. So the formula for gravitational potential energy is Eg equals mgh Newton meters or joules. Now, there's also energy due to change of matter into energy, and we call this nuclear energy. And these are the chemical reactions that take place in the sun. The sun loses 4 million tons every second. 24 hours a day, 365 days a year. Every second, 4 million tons that changes from matter into energy that comes to us in the form of heat and light. And the formula for it is E equals mc squared, Newton meters or joules, where c is the speed of light in vacuum. C is 3 times 10 to the 8th meters per second. And young people, don't worry. The sun is so massive it could lose this amount of mass for millions of years. Now let me go back to one of the graphs that we did earlier. And as I was saying, this is not a classroom setting. It's not easy to do this. Let's go back to this graph, because we were talking about potential energy. Well, what if you have a spring and you compress the spring? Well, if you let go, it could do damage. So a compressed spring has the potential and to do damage. We call this elastic potential energy. Now, if we get a spring and we put a mass on a spring, we get the force, and we measure the extension, and we can do that, and we can plot an fx graph. Since the graph is a straight line, then I can say f is directly proportional to x. When I change the proportionality sign into an equal sign, I must put a constant. F is kx, and k is the slope of the graph with its units. So the work done under this graph is the area of the triangle, half base times height, half x multiplied by the height, which is f. But f is kx. So half x times kx gives us 1/2 kx squared. 1/2 kx squared. And this is the elastic potential energy in a spring. Now, after the nuclear energy, and we talked about the energy due to position, well, I remember when I was in school, and one of my friends would not be paying attention. And a teacher, louder, a teacher gets a piece of chalk and tosses it at the student. We don't do this nowadays, by the way. This piece of chalk, because it's moving, it could do damage. And if it was more massive, it will do a greater damage. And so there is energy due to motion. This energy due to motion we call kinetic energy. Now, we said there is energy due to position, we call it gravitational potential. And energy due to motion, we call it kinetic energy. And now we will try to find a formula for kinetic energy. Imagine an object on a horizontal surface that's already moving with a v initial. And I apply a force, and this force increases the velocity of this object to v final. So this initially had kinetic energy. Here now it has a greater kinetic energy. Where did this energy come from? It came from the work done. The work that I did is equal to the increase in kinetic energy. So the gain in kinetic energy is the final kinetic energy minus the initial kinetic energy. The work done is the force multiplied by the parallel displacement. Well, the force is mass multiplied by acceleration. Now, I have to talk about this. That's from Newton's second law of motion, so I will review this with you as well. And I'll flip the board, and we do some review that is not really in this chapter, but Newton's laws of motion. The first law: an object at rest will remain at rest. An object that's moving with a constant velocity will continue to do so with uniform motion. Uniform motion means covering equal distances in equal periods of time in a straight line. So Newton's law, first law, says an object that's at rest will remain at rest, or experiencing uniform motion will continue to do so unless an unbalanced force acts on it. And by the way, this is also known as the law of inertia. Inertia is a resistance to a change in motion. Imagine yourself riding in a school bus, and the bus driver steps on the brakes. Well, you already have the velocity of the bus. If the driver wants to stop you, well, you resist and you move forwards. So inertia is a resistance to a change in motion. If the driver steps on the gas, you move backwards. The driver wants to take you forwards, you resist, you go backwards. And mass is a measure of inertia. So going back to Newton's first law, an object at rest or in a state of uniform motion will continue to do so unless an external unbalanced force acts on it. Well, what happens if an external unbalanced force acts on it? Well, this object will accelerate. Either way, acceleration could be speeding up or slowing down. If an unbalanced force acts on an object, this object will accelerate, and this acceleration is directly proportional to that force. As the force increases, the acceleration increases, and it takes place in the same direction of the applied force or the unbalanced force. And the acceleration, if the mass is larger, well, the acceleration is smaller. So the acceleration is inversely proportional to the mass. So we write it this way, proportional to 1 over mass. So acceleration is proportional to the unbalanced force. Acceleration is proportional to 1 over mass. We combine these, so acceleration is proportional to Fu multiplied by 1 over m. So F divided by m. If we change the proportionality sign to an equal sign, we must put a constant, F over m. And if we rearrange the formula, so we can say F is 1 over k ma. If 1 over k happens to be 1, then the formula for Newton's second law, which we were talking about, is ma. Newton's and direction will be the unit. And Newton's third law, for every action, there's an equal and opposite reaction. Now, Newton came up with another law of universal gravitation. If you have an object and another object, these two objects will attract each other with a force that's directly proportional to the mass of the first one, the mass of the second one, and inversely proportional to the distance that separates them squared. So if you have m1 and m2, there's a force of attraction between them, and they are separated by a distance d. So F is proportional to m1, F is proportional to m2, proportional to 1 over d squared. We combine them. It's proportional to m1, m2 over d squared. It's equal to a constant, m1, m2 over d squared. So the force of gravity, we call this constant g, m1, m2 divided by d squared. And g happens to be 6.67 multiplied by 10 to the minus 11 Newton meter square per kilogram square. So if this is the Earth and this is the object, then the weight of this object, or the force of gravity, is mass times the gravity on Earth. And we can also calculate the weight of the object by using this formula. The mass of the object, the mass of the Earth, multiplied by g divided by the distance that separates them squared. A little bit more of review, because we should not confuse uniform motion with uniform acceleration. Uniform motion is covering equal distances in equal periods of time in a straight line. If that is not the case, it's accelerated motion. Let's take the example of an object covering equal distances in equal periods of time in a circle. So it's covering equal distance in equal periods of time, but it is not in a straight line. So this is called accelerated motion. And the acceleration is in the direction of the unbalanced force, which is always towards the center in this case. We call this uniform circular motion. If I want to calculate the speed of this, well, if I take once around the circle, the distance will be the circumference. And the time for once around we call the period. So speed is distance over time, 2 pi r divided by t. And we know that period is 1 over frequency, and frequency is 1 over period. So I can substitute and use 2 pi r f. And you must have proved in class that this acceleration, which we call the centripetal acceleration, is v squared over r. And if you substitute this, you get 4 pi squared r over t squared. And if you substitute that, you get 4 pi squared r f squared. So this is a review to what you should know. And now we want to come up with a formula for kinetic energy. So the acceleration is v final minus v initial divided by t. The displacement, initial velocity plus final divided by 2 times t. Now I have to remind you that all the formulas that you were given are applicable only if the acceleration is constant. If the acceleration is constant, you cannot use v final equals v initial plus at. Displacement is vit plus 1/2 at squared. Displacement is vft minus 1/2 at squared. Or v final squared equals v initial squared plus 2 ad. And by the way, displacement is also the area under the velocity time graph. These formulas are out the window if the acceleration is not constant. What do we mean by constant acceleration? It means it has only one value. Let's assume the acceleration is 2 meters per second squared east. And I apply it on an object that's moving at 3 meters per second east. Acceleration of 2 meters per second squared east means 2 meters per second east. That means every second it will increase its velocity by 2 meters per second. So an object that's moving at 3 meters per second east, after 1 second it will be moving at 5 meters per second. After another second, 7 meters per second east. After another second, and so on. So displacement is average velocity, initial plus final divided by 2 times t. Well, t divided by t is 1. So I get this half here, and I get this formula. Now, imagine that the object started from rest. That means initial velocity was 0. Well, if it's not moving, it doesn't have energy due to motion. That means the kinetic energy is 0. That means the kinetic energy initial will be 0. And Vi is 0. Well, let's substitute in this form. This will be 0. Initial here will be 0. This will be 0. This will be 0. V final squared. So you come up with Ek is 1/2 mv final squared. So the formula then for kinetic energy is Ek is 1/2 mv squared. Newton meters or joules. So now we talked about gravitational potential energy, mgh. Kinetic energy, 1/2 mv squared. Elastic potential energy, 1/2 kx squared. And we also talked about nuclear energy, E equals mc squared. Now, Eg is mgh is not applicable at large distances from the Earth's surface. And for this, I've got to go back and do some review before we get into this. This is not a classroom setting. It is very upsetting, but we have to deal with it. We will do some graphical analysis. Physics teachers always like to come up with formulas that they can use. So if we're given a set of values, the independent is always listed first and then the dependent. Independent, dependent variable. And we also always list the independent variable on the x and the dependent on the y. So if we are given a set of values, we plot y versus x. If we get a straight line, we're laughing all the way. It's very simple. Y is directly proportional to x. Y is equal to kx. Once you take the proportionality sign, you have to put a constant. And you get the slope of the graph. K is the slope with the units. And you get your formula. So you substitute here for k, you get your formula that you can use. That's if you get a straight line. What if you get a power graph like this? Well, you make a guess. Your first guess should be y is proportional to x squared. So you square the x, square the units, leave the y as is, plot your graph. If you get a straight line, you're laughing all the way. You say y is directly proportional to x squared. Y is equal to kx squared. You get the slope with its units and you get your formula. What if you don't get a straight line? You try your second guess. You cube the x, cube the unit, leave this as is and plot the graph. You keep doing that until you get a straight line. Well, what if the graph looks like this? Then your first guess will be y is directly proportional to root x, or y is proportional to cubic root of x, or fourth root of x, and so on. So you try your first guess. Root x, root the unit, and you keep doing that until you get a straight line. If you get a straight line with this, you say, okay, y is directly proportional to the cubic root of x. Y is equal to kx cubic root of x, and you get your slope, you get your form. This is the graph that I want to talk about. This is the graph we're going to deal with. What if you get a graph like this? Well, your first guess would be y is proportional to 1 over x. You plot 1 over x. If you get a straight line, you're done. But if you don't get a straight line, if you get this, then you try 1 over x squared, then 1 over x cubed. If after plotting y versus 1 over x, you get this, then your second guess would be 1 over root x, 1 over cubic root of x. So remember that when we talk about some limitations to this formula. Gravitational potential energy is mgh. G on Earth is 9.8 meters per second squared towards the center. But what happens when you go way above the Earth's surface? Large distance. What happens to G? It's true your h is increasing, but your G is decreasing. And by how much? Well, let's look at this object in position 2. I can get the weight of this object by saying the force of gravity is mass times gravity. So F2 is mass times gravity at this point. But I can also say it's the force of attraction between this and the Earth. So this is also equal to G m Earth mass of object divided by the distance that separates them squared. The same with this object here on Earth. Mass multiplied by gravity on Earth will give you the force. And I can also work this out by saying it's G m divided by d1 squared, which in this case is the radius of the Earth. And this is using Newton's universal law of gravitation. Now I'm going to divide formula 1 by formula 2. I'm going to divide F2 by F1. So I'm going to divide mg2 by mg1. Well, m divided by m is 1. And I'm going to divide this by that. Well, here I change the division sign to a multiplication sign and flip this over. So you see G m, that will give me 1. And I get d1 over d2 squared. And I can rewrite this law as F2 divided by F1, G2 divided by G1, d1 over d2, the inverse, squared. This is generally referred to as the inverse square law. So let's look at gravity out in space. Let's say at a distance 2re from the center. That means re above my h. I will use this formula and see what I get. Well, if I want to find gravity here, so I can multiply mass by gravity by the height. So I want to work out gravity here. Well, g2 divided by g1 will be equal to d1 over d2 squared. So g2 divided by g on Earth will be equal to r Earth divided by 2r Earth, d1 and d2 squared. Well, r Earth, 1 over 2 squared will give me a quarter. And this GE, so I get G in that position is a quarter of the gravity on Earth. Well, let's substitute then in this formula, mgh. M, but G now is not 9.8. It's a quarter of 9.8 multiplied by RE. So 0.25 mg RE. Now, let's go to a distance of 2RE right here. That means 3RE from the center. So my H is 2RE, but the distance from the center is 3RE. Well, if the distance from the center is 3, by the inverse square law, then gravity will be 1/9, 1 over 3 squared. We substitute in mgh. M, 1/9 g, and the height above the Earth would be 2RE. When I do this, I get 0.22 mgRE. Well, watch this. This was 0.25. Now it's 0.22. What's happening? It's decreasing. But actually, I'm increasing. How can that be? I am supposed to increase. Now, if I go to a distance of 3RE above the Earth, that means 4RE from the center, G is 1 over 16, I'll get 0.19, still decreasing. What does this mean? It means that as I go further and further and further, I will end up with a gravitational potential energy of 0. So the gravitational potential energy at infinity is 0. Question then, how can I be increasing and I go to 0? Well, I'll try to explain this as simply as I possibly can. Let us assume here's the line, number line. Here's my 0, 1, 2, 3, 4, 5, 6, minus 1, minus 2. As I go this way, I am increasing. As I go this way, I'm decreasing. So as I'm increasing and approaching 0, then the formula should be a negative, not a positive, and I'm increasing from -6 to -5 to -4 to 0 and so on. So I'm increasing it this way. Let's take an example. If an object has -6 joules here, and I want to increase it to -2, I must do work. So the work done to increase the gravitational potential energy from -6 to -2, well, if I increased it to -2, then this is the final energy, and it was -6. So Eg final minus Eg initial. The final is -2, the initial is -6. Well, -6 is +6. And I end up with 4 joules. So if I give the object 4 joules of work, I will increase its gravitational potential energy from -6. So now we know the limitation of mgh, and we need a new formula for gravitational potential energy at large distances from the Earth's surface. And this is what we will try to do now. Let's assume here's the Earth, and you have a satellite at a distance r, and I want to move this satellite to infinity. And remember, the gravitational potential energy at infinity is 0. Well, remember Newton's law of universal gravitation? There's a force of attraction, which is g m Earth m satellite divided by r squared. Well, g is a constant, m Earth is a constant, mass of satellite is a constant, so this is a constant 1 over r squared. Well, that means Fg is directly proportional to 1 over r squared. Because when we change the proportionality sign to an equal sign, we put a constant 1 over r. So that means, from the graphical analysis that we took, the FR graph looks like this. And if I want to get the work done, I must get the area under this graph. And this area under this graph, we get it by integration. And by the way, you don't have to know integration, but I will go through it for the students who are taking calculus. If you have Fg and dr to get this area, and the integration will be the sum of all this. So the integral from r equals r to r equals infinity of f dr. That's the area under the graph, f dr. F is g m over r squared dr. Well, this is a constant. It doesn't have to do anything with the integration, so I take it out. So it's the integral from r equals r to r equals infinity of 1 over r squared dr. And here's where you really don't have to know this. The integral of 1 over r squared is minus 1 over r. We first substitute infinity, so minus 1 over infinity, minus, then substitute the lower value, minus 1 over r. Minus 1 over r is positive 1 over. 1 over infinity is 0. So this is 0. This is 1 over r. So we end up with this formula, g m over r. So this is the work done. Well, this work done is equal to the increase in gravitational potential energy of the satellite. Now, from a potential energy here to a potential energy there. Well, what's the potential energy here at infinity? The gravitational potential energy at infinity is 0. And the gravitational potential energy here is g m over r. So the increase in gravitational potential energy is g infinity minus gr, which is this, which I got it, the work done. That's the work done to increase. And if this is 0, then minus Eg is equal to this. That means the gravitational potential energy is minus g m over r, Newton meters. And this is our new formula. We don't use mgh. We have to use this when we are dealing with large distances from the Earth's surface. Now, if I have a rocket here sitting on Earth doing nothing, it has no kinetic energy, but it has gravitational potential energy, because our 0 of gravitational potential energy is at infinity. And this gravitational potential energy that it possesses is minus g m over r. If I want to get rid of this rocket, if I want to take it in outer space that it does not come back to Earth, I must give it at least plus g m over r. Why? Because if I give it plus g m over r and it has minus g m over r, if I add them, they add up to 0. So the escape energy then is plus g m over r. So escape energy is the minimum amount of kinetic energy to launch a rocket from the Earth's surface so that it completely escapes the Earth's gravitational field. On the Earth's surface, the rocket is bound to the Earth with this. And we can say, well, the binding energy is plus g m over r. Energy of escape must be plus g m over r. How do I supply this energy to this rocket? Well, I shoot the rocket up in space. So I give it a velocity. I supply this in the form of kinetic energy. So this means that 1/2 mv rocket squared must equal to this. In order to give it this, I supply it in the form of kinetic energy. And that gives me the velocity of escape. as the square root of 2gm over re. And you know the value of g. The mass of the Earth is about 5.96 times 10 to the 24 kilograms. You know re, the radius of the Earth. You can get this value. But also, the gravitational force of attraction between the two is given by g m Earth m rocket over re squared. And this is the weight of the rocket, mr ge. Mass times gravity gives the weight of the rocket. And you can work it this way. Well, multiply both sides by the radius of the Earth. So you multiply this by the radius of the Earth, and the mass of the rocket disappears. And you get gme over re equals ge. So look at this, gm over re. I can substitute for this ge. And that will give me another formula, 2 square root of 2 g Earth r Earth. And when you work out these values, you get the same escape velocity. So that is the escape energy. Now I will read this for you because I don't think it will be showing very well. My pen dried up at that time. Any rocket that is launched from Earth with a velocity less than 1.12 times 10 to the 4 meter per second upwards will either fall back to Earth or go into orbit around the Earth. So we talked about E equals mgh and its limitations, and we found that the better formula for satellites, the gravitational potential energy, is minus gmm divided by r. R is the radius of orbit. Let's talk about kinetic energy. If you have a satellite orbiting the Earth, there's an unbalanced force, which is the mass times the acceleration towards the center, mass times acceleration. Well, the force is also given by g, mass of Earth, mass of satellite, over r orbit squared, the distance that separates them squared. The mass of the satellite, the acceleration of the satellite, v squared over r orbit. Now, there's r orbit squared, there's r orbit, so you end up with m v squared equals gmm over ro. Multiply both sides by half. You get half mv squared is this. Well, 1/2 mv squared is the kinetic energy of the satellite. So now I have another formula for kinetic energy. It is equal to 1/2 gmm over ro. So the kinetic energy of a satellite is either 1/2 gme ms over r orbit or 1/2 mv squared. If you want the total energy, to work out the total energy of that satellite in orbit, well, you add the kinetic, which is this, to the gravitational potential, which is minus gmm over r. So 1/2 gmm over r plus minus gmm, you end up with minus half gmm over r. Now, to make physics easy for you, I summarized it. And it's very simple. Let's look at the summary. If you have a satellite sitting on the Earth's surface, doing absolutely nothing, it's not moving, kinetic energy is 0. But it has gravitational potential energy, minus gmm over r. And if you add this to this, minus gmm over r. And again, it's bound to the Earth. If I give it plus gmm over r, it will escape from the Earth. Easy. Now, an orbiting satellite. An orbiting satellite has a kinetic energy of 1/2 mv squared or 1/2 gmm over r orbit. Well, what's the total energy? Well, what does it have in gravitational? It has in gravitation minus gmm over r. What's the total? Add this to that, you get minus half gm. So the total energy of this is minus gmm over r, but for one in space, the total energy is minus half gmm over r orbit. So I hope it is clear. Now, for this orbiting satellite to escape the Earth's gravitation, if I want this orbiting satellite to escape, see, if I want this orbiting, this stationary satellite to escape, I must give it plus GMM. But for an orbiting satellite, I must give it plus half GMM over R. And this is known as the binding energy. So the binding energy is 1/2 GMM over R. Now, I don't know how much time we've taken so far, but I thought I might as well add thermal energy. When I was teaching in school, I remember doing this thermal energy in grade 9. So it's a junior topic. The quantity of heat. It's directly proportional to the mass, to the specific heat capacity, and to the difference in temperature. The formula, Q equals M times C times delta T. So they ask you calculate the quantity of heat when you heat some water from 60 degrees Celsius to 70 degrees Celsius, so delta T will be 10. And they give you the specific heat capacity for water and the mass, and you calculate the quantity of heat. But when there's a change of state, when you have ice at 0, if you heat ice at 0, it stays ice at 0. You heat it, ice at 0, until it changes to water at 0. There's no delta T. Well, your formula is Q is equal to mass times latent heat of fusion. And the same thing happens when water at 100 starts to boil. Water at 100, it changes to steam at 100. And there's no delta T. You use, for vaporization, Q is equal to mass times latent heat of vaporization. Let's look at the kind of problems they would give you. Let's say you are given something like ice at -4 and you want to change it to steam at 105, superheated steam. Well, when you heat ice at -4, the temperature rises to ice at -3, to ice at -2, to ice. The temperature is rising. This reminds me of the gravitational potential energy. As you're going from -4 to -3, you're increasing until it changes to ice at 0. Now, ice at 0 changes to water at 0. Water at 0, you heat it to water at 100 because you want to go to superheated steam. Water at 100, steam at 100. Steam at 100, steam at 105. Now, calculate the quantity of heat. Ice at -4 to ice at 0, mc delta T. C for ice, delta T will be 4. Ice at 0 to water at 0, mLF. Latent heat of fusion of ice. Water at 0 to water at 100, mc delta T. C for water, delta T is 100. And then water at 100 to steam at 100, change of state, mLV, and steam at 100 to superheated steam at 105, mc delta T, and that is for steam, and delta T would be 5. And they give you combinations of different problems. And then they give you a problem on heat lost and heat gained. They mix two liquids. The hot liquid will lose heat. The cold liquid will gain heat. Now, when I was teaching this topic, I remember I was very frustrated at one time, and the head of my department noticed that, and he said, "What's bothering you?" I said, "I'm teaching this topic. It's such an easy topic, but the students are not getting it." He said, "Hey, let me show you a trick." And he showed me this trick. He said, "Draw two boxes. These we call information boxes. Put the information for the hot object on top and the information for the cold object on the bottom. With the mass, specific heat capacity, temperature, mass, specific heat capacity, temperature. You're going to mix them together. You want to find, let's say, the final temperature. And let's say, for argument's sake, this is at 80 degrees Celsius. And let's say this is at 40 degrees Celsius. So this will gain heat, this will lose heat. Now, your delta T, AT minus T. But your delta T here is T minus 40. And you simply substitute. Quantity of heat lost is equal to quantity of heat gain. This is the one that lost heat. You got the mass, you got the specific heat capacity, and then the delta T. And this one gained heat, mass, specific heat capacity, and there's your delta T is T minus 40, and you get what you want. Now in physics, we do a lot of problem solving. I cannot do that because I'm not following a textbook, and I'm hoping that this goes universal. Remember, physics for all international. You could be in Australia, you could be in Africa, you could be in North America, wherever you are. I have to secure the permission of the co-author, and I'm sure he will agree, because all our life was dedicated to helping students. And if somehow we can put these notes on the internet and you can access them, I can do lectures on problem solving as well. Now stay safe, don't let your guard down, keep social distancing, wear your mask, wash your hands, and this period will end. But let's be careful. And once again, thank you for Light of All Nations and the staff of Light for All Nations that made this possible. I was hoping that a school principal would offer a classroom setting, and seeing I am of the old school, I prefer a blackboard over a whiteboard. I prefer working with chalk. Again, here is my email in case of any mistakes, in case someone wants to join, or whatever the case, you can get in touch with me. I cannot take any questions, but I hope this is helpful. Now, it all depends on how this video is received and your response. If we get a good response, we can go the next step further. Thank you very much, and God bless.